In the strip mill, pure lead is melted at high temperatures and passed through precision rollers to form a thin, continuous strip. This strip is then chilled for 24 hours to minimize microfractures. In the plate-making stage, the chilled lead strip is fed into expander tooling that stretches and perforates it into a mesh-like structure, forming continuous battery grids. These grids are coated with a specially formulated paste made from lead oxide, sulfuric acid, and additives. After application, the pasted grids are cut to size, stacked, and cured in a controlled humidity and temperature chamber to harden and strengthen the plates. During the assembly line stage, cured positive and negative plates are grouped into cells, with insulating separators placed between them to prevent short circuits. These plate groups are carefully inserted into the battery case in a specific arrangement. Intercell connectors are then welded by applying high pressure with weld tips and a surge of high current, ensuring strong electrical connections. Finally, a molded lid is aligned and permanently heat-sealed to the case, securing the internal components and ensuring a leak-proof enclosure. In the terminal burning process, intense flames are precisely applied to melt the battery terminals and internal posts. This fuses them together, forming a solid, permanent electrical connection that ensures reliable conductivity. A state of charge indicator is inserted into the battery's top, allowing users to check battery health at a glance. The case is then pressure tested to verify a secure, airtight lid seal. In the electrolyte fill stage, a carefully measured amount of low-strength sulfuric acid solution is added to each cell. This activates the chemical components and prepares the battery for its initial charging cycle. During formation, the battery is connected to a controlled charging system for 18 to 32 hours. This process activates the chemical reactions within the plates, forming the active material essential for energy storage. In the finishing stage, the initial low-strength electrolyte is drained after the formation charge. The battery is then refilled with fresh, high-specific gravity electrolyte, optimizing performance, ensuring proper conductivity, and preparing the battery for final testing, labeling, and distribution. Electric arc furnace melts scrap steel using high-temperature electric arcs. Scrap steel is added as raw material for melting process. Molten steel is poured from furnace into ladle for refining. Ladle furnace refines molten steel by heating and alloy adjustment. The VD/VOD plant removes dissolved gases like hydrogen, nitrogen, and carbon from molten steel on vacuum. This improves purity, enhances mechanical properties, and ensures better structural integrity in critical applications. Stripping of ingot involves removing the mold from solidified steel to prepare it for further processing like ESR or forging. The ESR process remelts ingots using electroslag refining to enhance cleanliness, reduce segregation, and improve steel's microstructure and mechanical properties. Ingot transport involves carefully moving solidified ingots from the casting area to the forging press. It ensures minimal thermal loss and prevents surface damage before forging operations begin. The 60 meganewtons press is a high-capacity hydraulic forging press used to shape large steel ingots into bars or other desired forms. With a pressing force of 60 meganewtons Mn, it can deform extremely large and heavy workpieces with precision. During forging, the ingot is heated to a specific temperature and placed under the press, which applies massive pressure to refine the grain structure, eliminate internal voids, and improve mechanical properties. This process aligns the grain flow with the shape of the bar, enhancing strength, toughness, and fatigue resistance. The 60 meganewtons press is essential for producing high-quality forged steel bars. Flame cutting uses a high-temperature oxygen fuel flame to precisely cut forged steel bars into required lengths, ensuring clean edges and minimal thermal distortion before heat treatment and further processing. Heat treatment involves controlled heating and cooling processes to alter the microstructure of forged steel bars. Common methods include annealing, quenching, and tempering. These processes improve hardness, strength, ductility, and toughness. Proper heat treatment relieves internal stresses, refines grain structure, and ensures uniform mechanical properties, making the steel bars suitable for demanding industrial applications requiring high performance and durability. HB hardness testing measures the Brinell hardness of forged steel bars by pressing a hardened steel or carbide ball into the surface under a specific load, assessing material strength and wear resistance. Ultrasonic testing uses high-frequency sound waves to detect internal defects and ensure structural integrity of forged steel bars. Face hardness testing to check surface hardness, particularly important for wear-resistant applications. Property testing such as tensile, impact, and fatigue tests to confirm compliance with mechanical property standards. Jorg's Marienhut manufactures over 500 different steel grades tailored to specific mechanical, chemical, and performance requirements. These include quality and special steels for applications such as automotive components, machinery, and energy systems produced with precise alloying and advanced metallurgical techniques. The production of high-quality steel from recycled scrap is a sophisticated and sustainable process, prominently employed at Georgs Marienhut GmbH. At the core of this process lies the electric arc furnace, EAF, which plays a central role in melting down sorted steel scrap into liquid steel. This method is significantly more climate-friendly than traditional blast furnace techniques, producing lower carbon dioxide emissions and supporting the principles of the circular economy. The journey begins with carefully sorted, high-grade scrap, which serves as the primary raw material. This scrap is melted in the EAF, a process that allows great flexibility in steel composition and energy efficiency. Once the scrap has been liquefied, the molten steel is transferred to the secondary metallurgy stage, where its chemical composition is precisely adjusted. Steel bars are produced in custom lengths ranging from 4,500 to 10,000 millimeters, meeting diverse application and processing needs. During secondary metallurgy, the steel undergoes degassing, desulfurization, and fine alloying to meet exacting customer specifications. This phase is crucial for achieving the desired purity and mechanical properties. Samples are regularly taken to ensure the correct chemical composition and microstructure of the steel, guaranteeing consistency and quality. 70% of steel output serves global automotive industry applications. 15% of the steel is supplied to the mechanical engineering sector, used in machinery, industrial components, and wind energy systems. After refining, the steel is cast into semi-finished products using a modern continuous casting system. Georgs Marienhut's 6-strand caster ensures efficient production with high dimensional accuracy. The continuous casting process at the Alchevsk Iron and Steelworks in Ukraine marked a significant step forward in the plant's modernization efforts, led by Primetals Technologies. As part of a broader campaign to upgrade production capabilities across the facility, 2 identical 2-strand slab casters were installed between 2003 and 2005. These casters were designed with a combined annual casting capacity exceeding 5 million tons, representing a major leap in efficiency and product quality. The project began with the demolition of existing buildings at the caster site, followed by the excavation of a massive pit to house the foundations and scale pit for the new slab casters. Erection of the first support structures for the casting bay commenced soon after, and within a tight project timeframe of just 17 months. The first slab was successfully cast in August 2005. Shortly after, the second slab caster was brought online, further enhancing production capacity. Primetals Technologies oversaw the entire project under a service contract that ensured fast, efficient, and uninterrupted implementation, minimizing disruption to ongoing steel production. The continuous casting line included advanced features such as a twin-station ladle furnace for adjusting steel composition and temperature, and vacuum degassing capabilities for higher purity when required. To ensure optimal performance and product quality, the casters were equipped with state-of-the-art technological packages. These included MoldExpert for enhanced mold monitoring, a dynamic secondary cooling system, DX model, and Dynagap soft reduction technology for minimizing internal defects in the slabs. Additionally, a computer-aided quality control system was integrated to continuously monitor and manage the casting process. The slabs produced are stored and retrieved efficiently in a managed yard using an automated computer system, contributing to streamlined logistics and improved plant operations. Dedicated workshops were also established for the maintenance of caster components, ensuring high availability and reliability of the equipment. Steel forging is a traditional, yet highly sophisticated manufacturing process that transforms raw steel into strong, durable, and precisely shaped components used across numerous industries such as automotive, aerospace, construction, and machinery. The forging process involves shaping metal using compressive forces, often delivered by a hammer or a press, to alter its shape without removing material. This results in parts with superior mechanical properties compared to those made by casting or machining alone. The process begins with selecting the appropriate steel grade. Steel used for forging can range from carbon steel, alloy steel, stainless steel, to tool steels, depending on the desired mechanical properties and final application. The quality of the raw steel is crucial, as it directly affects the strength, toughness, and wear resistance of the forged product. Heating is one of the most critical stages in the steel forging process, as it prepares the metal for deformation by making it ductile and malleable. Steel billets or bars are heated to a specific temperature range, typically between 1,100 degrees Celsius to 1,250 degrees Celsius, 2,012 degrees Fahrenheit to 2,282 degrees Fahrenheit, where the steel's crystal structure becomes more receptive to shaping without cracking or breaking. At these elevated temperatures, the steel's internal grains soften, allowing the metal to flow under compressive forces during forging. Achieving uniform heating throughout the billet is essential. Uneven heating can cause thermal gradients, leading to internal stresses, microcracks, or unwanted microstructural changes such as grain growth or segregation. These defects can weaken the final forged part and compromise its mechanical properties. To ensure homogeneity, billets are soaked at the target temperature long enough to allow the heat to penetrate evenly from the surface to the core. Modern forging operations typically use two main types of furnaces: induction furnaces and gas-fired furnaces. Induction furnaces heat steel billets rapidly and efficiently by generating eddy currents inside the metal using electromagnetic fields. They offer precise temperature control, fast heating cycles, and lower energy consumption, making them environmentally friendly and cost-effective. Gas-fired furnaces use combustion of natural gas or other fuels to generate heat. These furnaces provide consistent heating for large batches of billets, with modern designs incorporating advanced burners and insulation to maximize thermal efficiency and reduce emissions. Both furnace types are often equipped with sophisticated control systems and sensors to monitor temperature in real time, ensuring optimal heating conditions for high-quality forging outcomes. Open die forging, also known as free forging, is one of the oldest and most versatile forging processes. In this method, a heated steel billet or workpiece is placed between two flat or simply shaped dies, and mechanical or hydraulic hammers or presses apply compressive forces to deform the metal. Unlike closed die forging, the dies in open die forging do not fully enclose the metal, allowing the metal to flow freely except where it contacts the dies. The process begins by heating the steel billet to a forging temperature, typically between 1,100 degrees Celsius and 1,250 degrees Celsius, to ensure the metal is sufficiently ductile. The heated billet is then positioned on the lower die, or anvil. The upper die or hammer strikes the workpiece, compressing and shaping it. The blacksmith or operator manipulates the billet between each blow, often rotating or repositioning it to achieve the desired shape and dimensions. Open die forging is particularly well suited for large and simple shapes, such as shafts, discs, rings, and bars. It is commonly used for custom or low-volume parts where flexibility is needed because the dies can be simple and easily adjusted or replaced without the need for complex tooling. The process allows for gradual shaping and refining of the metal, providing excellent control over the grain flow and mechanical properties of the forged part. One key advantage of open die forging is the ability to produce very large components that would be difficult or impossible to forge using closed dies due to size limitations. It also allows for varying cross-sections and complex geometries by sequential forging steps. However, the process is labor-intensive and requires skilled operators to control dimensions and tolerances. The resulting forged parts benefit from refined grain structures and improved strength and toughness due to the controlled deformation and realignment of the metal's internal grain flow. During closed die forging, excess material called flash is squeezed out along the die parting lines. After forging, this flash must be trimmed off. The trimming ensures the forged part meets dimensional specifications and improves its appearance. Post-heat treatment. Forged parts often require surface finishing operations such as grinding, machining, or polishing to achieve final dimensional accuracy and surface quality. Some parts may receive coatings or treatments such as painting, plating, or nitriding to improve corrosion resistance or wear performance. Die forging plays a critical role in the production of high-strength components for heavy-duty applications, such as those used in the railway industry. One such example is the forging of a locomotive chassis component, weighing approximately 100 kilograms and made from steel. This process involves both pre-forging and precision die forging, requiring significant expertise, coordination, and the use of heavy machinery. The initial stage of production begins with the pre-forging operation. The raw steel workpiece is roughly shaped using a pneumatic pre-forging hammer. This particular hammer, built in 1959, delivers a striking force of 900 kilojoules. Although the equipment is decades old, it remains highly effective in distributing the material uniformly in preparation for the final forming. This stage ensures that the bulk of the steel is already in the desired configuration before it undergoes the more precise die forging process. Following pre-forging, the component is subjected to die forging using an electro-hydraulic drop hammer with a striking energy of 1,250 kilojoules. This hammer, manufactured in 2003, performs the detailed shaping of the part within a specially designed die. Interestingly, the size of the component exceeds the optimal capacity for this particular hammer, presenting a unique challenge. To achieve the final shape and required mechanical properties, more than 100 hammer blows are necessary. The forging process requires multiple thermal cycles to maintain the steel's malleability. Initially, the workpiece is heated to around 1,200 degrees Celsius and then reheated twice more in a gas-fired forging furnace during the die forging process. These reheating steps are essential to keep the material workable and prevent defects like cracking or incomplete filling of the die. After each major forging step, the component undergoes a trimming process to remove excess material known as flash, which forms around the edges during die forging. A 400-ton hydraulic press, built in 1982, is used to perform this task. The trimming operation is carried out 3 times in total, ensuring a clean and precise final shape for the forged component. Handling and transporting the hot and heavy workpiece during the forging process is no small task. A specialized forging manipulator designed to manage parts weighing up to 300 kilograms is employed to maneuver the component safely and accurately between stages. This equipment ensures not only safety, but also the efficiency of the forging process. One of the most striking aspects of this operation is the seamless teamwork among the 3 specialists involved. Their coordination, technical expertise, and mutual support are vital to the success of the process. Each team member plays a specific role, contributing to the smooth execution of complex tasks under intense heat and pressure.